So, welcome everybody. I'm very pleased to be able to welcome you here tonight on this beautiful, beautiful spring evening. And I'm Neil Calder. I'm the Director of Communication here at SLAC. And here we have a fantastic evening, a wonderful lecture, robots, fantasy, and reality. Before I get on to actually talking about tonight's lecture, I'd like to welcome some very special guests here who deserve our applause and appreciation. The first group are the people kind of inconspicuously dressed in bright orange out there, who are the Woodside and Coleman High School robotics team, Team 100. And these guys have done a most amazing job because they won through on this big national robotics competition. They built a robot which is very endearingly called Tubosaurus Rex. And they made it through to the national finals just recently in Atlanta and did extremely well winning right through to the quarterfinal stage of the national competition. So round of applause for The other people who I'd like to welcome are the Boy Scouts from Menlo Park, who are wearing in themselves a particularly noticeable uniform. This is Troop 222. Welcome here. And I'd also like to mention one person in particular, who is young Hunter Thompson, who's my neighbor. And I know he's very keen on robots. He's just a young man, but I'm delighted to see him here. Welcome, Hunter. So on tonight's talk and tonight's speaker, what I know about robots is very little other than it's a kind of dance I tried to learn how to do a few years ago without much success. But our speaker tonight, David Grossman, is a physicist, which is a good thing around here. That David did his doctorate at Harvard. He then went on to work on particle physics at a legendary accelerator facility in Frascati in Italy. But then David had some kind of midlife crisis, I guess, because he abandoned particle physics and went to work for IBM. Anyway, at IBM, he spent 25 years subsequently working on robot design and artificial intelligence, so he knows what he's talking about. David has also done work at Stanford in the engineering department and at the medical school, and it says here that in his spare time he builds huge cosmic ray detector arrays in his garage at home. I had to read that twice, but I think it is true, isn't it? Good. So I'd like you all to give actually, before we give a very warm welcome, I'd just like to point out these safety emergency information. Essentially, you can see, beware of the exits. There's 2 exits here at the top and also 2 exits here at the side. Follow the building residents, which I guess is me, out of the building. Earthquake, we know. Event of emergency, really, the only thing you should know is dial 9 and then 911 on any phone. So, could we have a very warm round of applause for our speaker tonight, David Grossman. David.
Well, much has been written and much has been said about robots. And the purpose of this talk today is to equip you to be in a position where when you look at the future of robotics, you can assess the difference between what's fantasy and what's reality. I have to start with a definition of what is a robot. And certainly most people have this view that a robot is something that looks human, or at least it looks animate. It behaves in an animate fashion, but it's actually inanimate. And it's in some sense surprising that an animate object could be animate. So with that in mind, I have a list of some of the attributes of animate behavior: animate appearance, But to sum it all up on this, the definition that I'm going to use as I go through this talk is anything that's surprisingly animate behavior. And to sort of paraphrase Santayana, in order to understand the robots of the future, it's a good idea to look at the robots of the past and the robots of the present. The catch here is the word surprising, because what's surprising in one time may not be surprising later on. For example, I submit to you that if you could have taken a washing machine back to the Middle Ages, assuming, of course, that you had a place to plug it in, it would have astonished everybody because it would have replaced the animate function of washing clothes by beating the clothes with rocks in the river. So people would have been surprised. And they're not surprised now. You look at it and you say, well, that's not a robot any longer. Now, where did the word robot actually come from? It's a Slavic word, and it means simply work. As it turns out, in the early days of the Soviet Union, there were work camps called robot camps, and the work was not voluntary, so the word has also taken on the connotation of forced work or drudgery. The word came into English primarily as a result of a play, R.U.R., Rossum's Universal Robots by Karel Čapek, a Czech author. In it, the inventor, Rossum, has invented artificial protoplasm with which he can build people for a price of about $50 a piece. And so all the countries of the world use them to staff up their armed forces, after which the robots realize they don't need the people anymore, so they kill all the people. Fortunately, with the exception of two, because later on the robots realize they can't replicate themselves, and those two then turn into Adam and Eve so that the whole cycle can start all over again. But the emphasis here is that it's artificial protoplasm, not metal. And in the same spirit, other things which are not metal have been considered robots. The ancient Jewish legend of the golem, create a lump of clay molded into a human figure by Rabbi Ben Lo, or also Dr. Frankenstein's monster, which uses biological parts to make a creature. That story is written by Mary Shelley in 1818. I'll say a little bit more about Mary Shelley later on in this talk. By the way, if you've ever read the book, you'll realize that the films based on that book are very different from the book itself. Now, one of the attributes I listed earlier that could be surprising in an inanimate object is talking. And the earliest example of a human-made object which could talk is this statue, Memnon, son of dawn. A huge statue, about 80 feet tall. Every morning when the sun rose, it would emit chirping noises as it heated up. It was talking. Well, at least the priests said it was talking, and they could interpret exactly what it was saying. Much later, Thomas Edison patented the first talking doll, which would have been surprisingly animate in its day. And then along came Texas Instruments' Speak and Spell in 1978, which could talk, and it removed the surprising element, so that we no longer consider a talking machine to be in any way surprising. Parenthetically, let me say that in the Ozma of Oz, which was a sequel to The Wizard of Oz, Dorothy comes across the mechanical man. You wind him up and he can walk or talk. But rather like ex-President Ford, he can't do both at the same time. Now, another example of what would be surprising in its day is articulated arms. Humans have articulated arms, and here's the first statue that actually had articulated arms. Of course, they only had 1 degree of freedom. And by comparison, the human arm, counting all the fingers and all the joints and so forth, has about 27 or 28 degrees of freedom. Still, 1 is a start. Starting in Padua, Italy, around the year 1344, a number of cathedrals in Europe were built with animated figures. Shown here are 2 scenes from the one in Prague, and which was enhanced several times over a 400-year period. But there's also a very famous one in Bern, Switzerland. Typically every hour, figures march around, bears march, scepters are moved, roosters crow, and so forth, where the skeleton on the right jiggles up and down. Around the same time, mechanical paintings became very popular. Now, in some sense, I wouldn't consider this to be a robot because it doesn't perform any animate function. On the other hand, you have to imagine the balloon drifting back and forth, the windmill turning, the train moving, the boat moving, and of course, the clock moving. And a clock moving is, of course, a sequel to the first pendulum clocks, which were, the concept came from Galileo, but was perfected by Christian Huygens. And that, in turn, was the automated version of the clepsydra, which goes way back in history. I don't consider any of these to be robots. But here's something that certainly qualifies as a robot, an android figure created just as the Industrial Revolution was taking off. Small number of people like Jacques Droz used the technology instead to build mechanical automatons. Now here, there are, inside the seat, in here, hidden away, are rotary cams with cam followers. And as the cams turn, the figure moves. It can write, make pictures, write poems, periodically lifts the pen up, dips it in inkwell, but it's more than just 2 or 3 degrees of freedom like a plotter. The feet move back and forth, the head turns, the eyes open and close, and they move from side to side, and the chest breathes in and out. And then for 200 years, this technology was lost until an inventor came along in Switzerland very recently by the name of Francois Junot, and he has built this machine. It's one of many machines he's built. Here are the cams, and for some reason it's frozen at the moment. There it goes. But you can see that it performs the function of a plotter, but you'll also see the feet moving and the eyes moving. If you want one of these figures, you can buy it for about $80,000 each. And I have to emphasize there is no hidden computer in it. It is completely mechanical. Around the same year, Jacques Droz also built this piano player. The piano player, again, has hidden in the base rotary cams, which pull on tendons, which actually pull the fingers so that the fingers really play the piano. There's no hidden music box in this, but in fact, cylinder music boxes were invented just about 23 years earlier, and they in turn were the sequel to cathedral carillons, which over the years, as clocks got improved, started playing notes automatically every hour. Interesting thing here is that this, in 1773, is technologically more advanced than Disneyland with the robot bear jamboree, because here the bear just appears to be playing the piano and there's really a hidden music box. The player piano itself was invented by Fourneau in 1863 and perfected by McTamaney around 1881. And of course, it doesn't have any human appearance, but it's replacing the human function, and therefore I consider it surprisingly animate in its day. This leads to the general topic of robot music. Back around 1728, the richest man in the world would have been Charles VI. And if he wanted to hear music, he would simply command the performance of the orchestra in the Vienna Symphony Hall. This is not a picture made in 1728. They didn't have photography or color film then. But in some sense, you can consider the Sony Walkman to be a robot orchestra. Or more recently, you can consider the Apple iPod and its successors to be robot orchestras. And I will digress here, as I want to do on a number of occasions in this talk, just to mention that for those of you who are unaware, Apple Corporation actually got its start in this auditorium a little more than 25 years ago when the Homebrew Computer Club was meeting here, and one demonstration was by Steve Wozniak of a machine he called Apple, and another attendee was Steve Jobs. Here I consider this to be one of the most remarkable robots of all time, Vaucanson's duck. It's used for stage shows in 1738. Here you see the rotary cams exposed, but imagine that the duck would have feathers so it looked like a real duck and that this is all covered up. People would pay money to come in, to sit down in an audience, and then the operator would turn the machine on, and the duck would look around the room, flap its wings a bit, stretch its neck, and quack. And the operator would realize the duck was hungry, so he'd take a dish of food and put it right in front of the duck. Almost immediately, the duck would start eating the food. And as he swallowed the food, you could see the peristaltic motion of the neck muscles. And then he would stop periodically, quack, look around, flap his wings. And then when he finished, he had eaten very, very quickly. You could see from the pained look on his face that he'd eaten too fast. He had a stomachache. He looks more and more uncomfortable, and suddenly with a little grunt, he relieves himself on the table. A chemical smell spreads out through the room. Wild applause for Vaucanson's duck. A little bit later is von Kempelen's Turk, one of the most famous robots of all time, but a complete fraud. This was a chess-playing robot that played in a lot of exhibitions. At the beginning of the match, the operator would open this door to reveal a network of gears so dense you couldn't possibly see behind it, but then he'd open a back door and shine candlelight through so you could see there was nobody hiding behind this section. Then he would lock up the back door, put the candle away, open this door and this drawer so you could see there's nobody hiding in here either. And he'd close it all up. The machine would begin to play with whirring and clicking noises. The Turkish figure would reach out and move pieces. Played a number of exhibitions throughout Europe. One was against Emperor Napoleon. Napoleon was beaten in the first match. This was the final position. In the second game they played, Napoleon started cheating. When he made an illegal move, the robot reached out and took back Napoleon's move. And when he did it a second time, the robot swept all the pieces onto the floor. Now, how did it work? Well, of course, there was a small chess master hiding inside it. Many people speculated on the construction. One of the more accurate speculations came along in 1836 by Edgar Allan Poe in a magazine article in the United States, and he had never even seen this. He wasn't exactly right, but anyway, the idea is that initially there's a person hiding in this compartment, and as soon as he hears the back door close, he stretches out in a L-shaped position behind the drawer. The drawer doesn't really go all the way back. And then when everything's closed, he makes himself comfortable. He has a pantograph linkage that controls the robot arm. The pieces have magnets underneath them, and there are springs above the chess master so he can see when pieces get moved. And he has, of course, a candle in there so that he can see what's going on, and he has a little chess set. Now, the first actual chess-playing robot was built in 1912. An electromechanical machine was built by Leonardo Torres y Quevedo, shown here being demonstrated to, I think that's either von Neumann or, what's the other guy's name? Norbert Wiener. I don't know which that is. All it could do was play a king and a rook against a rook. But remember, no computer involved, purely mechanical system. By the way, Quevedo also was responsible for building a cable car that runs above Niagara Falls so the tourists could go there. In general, in the very early days of electronic computers, they were ascribed human characteristics. They were typically called giant brains. So here's the first large-scale electronic computer, ENIAC. And if it's a giant brain, then it must be animate. So, of course, it's surprisingly animate, a robot. Or another example is the ability to have feedback so you can respond to the environment, to adapt to the environment. The first such examples are probably ships that had some sort of automatic system for sensing the direction of the wind and adjusting the direction of the rudder. But here's an example from 1745, a windmill that would sense the direction of the wind and automatically steer the windmill in the optimum direction. Now, the next major topic of this talk is to get into the work of the artificial intelligence labs around the world. There are 4 subtopics: intelligence, mobility, visual recognition, and dexterity. The people who coined the phrase artificial intelligence, or AI, that was John McCarthy at MIT and John McCarthy at Stanford and Marvin Minsky at MIT. And they were predicting that within 10 years, computer programming would get so good it would be the world champion. Well, a pretty good chess player by the name of David Levy didn't believe this, so he offered to bet £1,000 that the machine wouldn't even be able to beat him in 10 years. And 10 years later, he won that match. He also explained what are the pitfalls of computer chess and why it might take a much longer time. And in fact, it took about another 20 years or more until finally along came Deep Blue, and it beat Kasparov in 1997. And now computer chess is at world-class level. Here's a wonderful exercise in mobility. The Beast from Johns Hopkins Applied Physics Lab in 1972. This is a battery-powered vehicle that roams around the corridors. It has a sensor in front, so if it comes to a flight of stairs going down, it will not fall down the flight of stairs. But it'll wander into people's offices if they leave the door open. And more importantly, when it senses that its battery level has gotten too low, a tape recorder switches on. It starts repeating, "I'm hungry, I'm hungry." Then it sidles up to the wall and searches along the wall looking for a plug to automatically plug itself in to recharge the batteries. Around the same time, a project was started at Stanford University in the AI lab up in the hills at those days. It was a battery-powered vehicle with a television camera and a radio link back to a much larger computer. The concept was to have this drive autonomously all the way to San Francisco Airport, a distance of 23 miles. After many years of research, somebody did a PhD thesis where, well, actually in the first demonstration, while everybody watched, it fell off the stairs in front of the lab. But in the subsequent demonstration, it was able to navigate around the parking lot while avoiding artificial trees made of cardboard. It would take a picture, then move 10 feet, take another picture, do the stereo reconstruction to find out where the obstacles were, then move another 10 feet and so forth, achieving ultimately an average speed of about 23 miles per year. But I will say more about this later on. At the same time, there was a project at SRI, headed by Charlie Rosen and Nils Nilsson, called Shaky the Robot, so-called because it would roll to a new location and then it would kind of shake back and forth until it damped out. Also battery-powered television camera, but here it's given a task in robot planning. The task is to knock the block on the floor, and it figures that in order to do that, it has to find the ramp, move the ramp into position, then roll up the ramp, and then knock the block on the floor. So what it's doing is planning, and that's surprisingly animate. At the tail end of World War II, there was a need to develop master-slave robot arms because people were developing nuclear weapons. And what you see here is an operator with two master arms looking through a lead glass shielding window with a fabrication of some plutonium parts on the inside of the shielding window. This is a schematic view of it. One of the problems with this is that there was no force reflection, so that he couldn't tell how hard he was grasping. So if you're holding a test tube, if you grasp too hard, you crush it, and if you don't grasp hard enough, you drop it. So within a few years, it was necessary to add force reflective servos. Henry Ernst took this machine, one of these machines, and replaced the operator with some motors attached to a computer in 1961 as a PhD thesis. He also added sensors in the robot hand and programmed it to grope around a table, feeling for blocks, and then either stacking them up or dropping them in a large box. He was, by the way, then hired by IBM with the stipulation that he would never for the rest of his life work on robots again. 13 years later, MIT had progressed to this level, the so-called copy demo, in which an operator has built a building out of blocks. The camera looks at it, figures out how to build it, and then it builds a copy of it. Or, if you wish, a mirror image copy of it, whichever you prefer. Around the same time, Stanford was working in the area, and this is the so-called Stanford arm built by Vic Scheinman in 1972. And let me mention that Vic Scheinman is here today. Where is he? He's hiding. So there he is, over there. So at the end, when you start asking me questions, you can split up and ask some of him questions. After this arm was built and attached to a large computer, Lou Paul programmed it to solve the instant insanity puzzle. The instant insanity puzzle is to stack these blocks up so that each column you look at has all four different colors. And you can see that the television camera can only see 2 or 3 faces at a time. So it takes about 5 minutes for the robot to turn blocks over in different orientations until the camera sees all the faces. Then it takes about 1 millisecond to solve the puzzle, and then another 5 minutes to stack it up in the right answer. And hopefully it doesn't accidentally drop the blocks in the process. So in doing this, I had to write a program that was very general, that could turn absolutely anything upside down, provided that it was a 1-inch cube. Around the same time, Donald Mickey at University of Edinburgh programmed up the assembly of the toy truck out of its 7 component parts. There's 4 wheels, 2 axles, and a chassis, initially in an aimless heap on a black background. The robot here consists of an XY table on the whole floor, and then this arm that comes down about this size, which can move up and down, turn, and grab things, and so forth. All attached to a very large computer. The camera looks, it figures out what's sticking out the side of the white pile of stuff, grabs it, palletizes it. That takes a while. Then when everything is palletized, then it does the assembly. If it can't find anything it recognizes on the periphery of the white blob, instead it smashes the blob, and then things scatter. Well, it was at this point that the British Research Council National Research Council in England decided that maybe this was a foolish way to spend money, so they commissioned Sir James Lighthill to evaluate whether or not robotics research was useful. And Sir James Lighthill, a famous mathematician, he said, well, if you look at the way people are working on robots, they're all men doing the research, and all these robots operate in a child's world as seen by a man, and the stimulus is the urge to compensate for lack of the female capability of giving birth to children. This is actually an early version of the report. The report then got edited before the final version came out. But you can imagine the National Research Council after this stopped the funding for many, many years. But it also got people thinking more in terms of useful robots. And immediately at Stanford, they turned to the assembly of a water pump, which involved bringing the space into position, then getting 2 locating pins from their holder, put them here, pick up a gasket, put it on the locating pins, get the top of the pump here, which is hard to see on this, then pick up the power screwdriver, get a screw, run in 4 screws, put down the power screwdriver, return the 2 pins to the locating holes, get the power screwdriver, and run in the last 2 screws. Total process about 5 minutes and about 50% reliability. But that's great progress. I mean, this is really attempting to do something that demonstrates something useful. And around the same time, a project was started at IBM to build a robot that could do assemblies in IBM, perhaps something like a typewriter rail assembly, a very dexterous machine that we called Klutz. And what you see here is that around this time, it was programmed up with power tools and parts to assemble 25 pieces of a typewriter. By the way, earlier, just to make sure the machine was working, I programmed up a demonstration that it could also build a toy, Mattel Build-A-Train out of 16 parts. However, with regard to the typewriter, let me mention that a typewriter in 1975 had about 1,000 parts. A printer today has about 40 parts, and therefore it's about 50 times, or whatever the number is, 25 times easier to assemble, and therefore whether it's assembled by a robot or by a machine or in fact by a person is of much lower importance. And this is the general topic of whether or not one can redesign something so that you don't need robots to do it in the usual sense. And I'll come back to that topic later on. This gripper on our robot had a sensor between the fingers, infrared beam, so you could program it to detect when something was between the fingers. So you could program it to just sit there all day long waiting for a fly to fly between the fingers and grab the fly, which would make it the world's 2nd most expensive fly catcher. And of course, the question is, if that's the 2nd most expensive flycatcher, what's the world's 1st most expensive flycatcher? I don't know if anybody here knows the answer to that, but I will tell you the answer. The answer is Barry Bonds. And I'll digress again since I'm on the subject of baseball. See, there's a theme here, fantasy versus reality, and you see a lot of press reports. And a lot of it you really should be very skeptical of. For example, this is claimed to be a robot batter that can hit a ball thrown at 200 miles per hour. And you probably can't see, but there's a guy standing inside the cage back here. He must be very, very confident because I mean, obviously, the ball will never get fouled off, right? Well, if the ball will never get fouled off, what's this doing here? What's that doing there? What's that doing? And why are they using tennis balls? Why don't they use a hard ball? So I don't believe that. I don't even think there's a machine that can throw a ball at 200 miles an hour. And this is claimed to be able to catch the ball at 200 miles an hour. And I'm sure, Vic, you'd agree that if a ball really hit that at 200 miles an hour, the electronics would be hopelessly smashed. I can't believe that it has the ability to catch anything. Another example of athletics, by the way, this is a real one. At University of Pennsylvania, Russell Anderson programmed up a robot, shown up here, with a long stick attached to a paddle to play a respectable game of ping pong using TV cameras. It's on a miniature table, so it's not the real game of professional table tennis, but it's an impressive demonstration nonetheless. Now, back in 1975, I programmed up what I think was the first demonstration of a robot putting components in cards, dual inline packages or DIPs or flat packs. Up until that time, all card assembly was done by people. And in fact, in those years, well, I'll come back to that in a moment, 5 years later, we had built a machine that could actually assemble cards in an industrial setting. And nowadays, of course, if you look, all cards are assembled this way. That is to say, robotically assembled. As I was starting to say, 5 years earlier, we had put together a robot songbook in our project. And one of the songs dealt with this. It had a line in it, you don't put dips in, you don't wrap wire, so those who wrap it cannot retire. It's to the tune of Old Man River. But the reality is all those who did wrap wire and put dips in, they all have retired because robots are doing those jobs. Here's a picture in 1983 when IBM was marketing this robot. Actually, that's not the first time IBM marketed a robot. 1978 was the first time. Back in 1983, I had a lot more hair and it was a different color. It turns out that programming a robot with sensors to pick up a raw egg is a lot easier than you might think. And we had done it about 8 years earlier. And I remember very well, we were so pleased when the robot picked up the raw egg without breaking it. And then we said, OK, now command it to crush the egg. And it strained, and it strained, and it strained, and the fingers broke. Now, some of you maybe were unaware that IBM ever sold robots. But then I would guess that most of you are unaware that many years earlier, IBM actually sold a precision cheese slicer. So robots is much more plausible. Now, in terms of assembling complex things, you may think that an assembly like this of a steering mechanism could only be done by a human or a robot. But in fact, that's not true. The technology is well established for building very complicated room-filling machines called transfer machines. They cost multiple millions of dollars. This is the view of such a machine. Incredibly complicated. Let's go back to that. Incredibly complicated. And one of the features of such a machine is that if you make a very minor change in the object that you're assembling, the machine can't cope with it at all, so that it has no adaptability. So I wouldn't consider a machine like that to be a robot because it's really, in my opinion, not surprising and not animate. In fact, when I look at a machine like that, it reminds me of the cartoonist Rube Goldberg, and I thought I'd include one of his cartoons here. This is a machine that automatically reminds you to mail a letter to your wife. And the way it works is that when you pass the shoe repair place here, there's a shoe hanging down, so you've got the strap on your waist, and it hooks that, and the boot then kicks the ball over the goalposts into the net, lifting the watering can, watering down the tails of the coat, which on a pulley system pulls up the door, the bird comes out, goes for the worm, and pulls down the message that says, mail your wife's letter. But here's a Rube Goldberg invention that's a heck of a lot earlier. An automatic doorman, I submit to you, in its day, if it had ever been built, it would have been considered surprisingly animate. The concept is that you build a fire at A, and through some heat transfer mechanism, compartment B heats up. The water is then pushed over the siphon into bucket D, and through an arrangement of pulleys and capstans, the door opens. And later, when the fire goes out, the doors close. Automatic doorman. One of the most famous machines that came out of the Industrial Revolution is the Jacquard loom, which semi-automated the process of weaving. It has, driving it, a system of punch cards, a whole sequence of punch cards, and the holes determine which threads get lifted and which threads get lowered at each step as the shuttle moves back and forth. Now, this gave rise to a whole lot of other things. The first thing it gave rise to was that a lot of people were afraid it was going to take away their jobs. And therefore, an organization established itself known as the Luddites, and they went around breaking into factories and smashing machinery of this type. It got to be a sufficient problem that in 1811 the British government sent out troops to Nottingham. They rounded up 50 Luddites, executed them, and the problem went away. The second thing is that Charles Babbage was the inventor who invented the difference engine, a mechanical machine, but then he followed it up with a programmable computer that he called the analytical engine. He never actually got it built, but he put together a lot of plans for it. And it was to be programmed using a sequence of punched cards. And the first programmer for it was a mathematician by the name of Ada Lovelace. And this ties together with Mary Shelley earlier, because Mary Shelley was married to the poet Shelley. And they were good friends with Lord Byron and his wife. And in fact, Ada Lovelace is the daughter of Lord Byron and his wife. And the third thing worth mentioning at this point is that this idea of using punch cards was then the way that Herman Hollerith applied to doing the census tabulator in 1890, and eventually his company grew into IBM. Predating the AI lab work on useful robots was the work of George Duval and Joe Engelberger, who saw the need for building industrial robots that could function in car factories, lifting the heavy welding gun that weighed about 70 pounds. In those days, it was hard to convince American companies to use it, so they went to Japan, had no difficulty convincing people, and now ultimately, automatic robots of this nature are used in car factories all around the world. And if you've never been to the NUMMI factory in Fremont, I suggest that you go to their website, look it up, NUMMI. The only requirement is you have to be at least 10 years old to go there, and you'll see lots of robots. One of the things we did in the robot project at IBM was we did the feasibility study for a medical robot called RoboDoc, which was to grind out the inside of the femur for an orthopedic hip implant operation, and it could grind it out very accurately. But there are many other instances of robots in medicine, and I'll show a few. Here's a scrub nurse that has a speech recognition capability. So you say scissors, you reach out and it slaps scissors in the surgeon's hand, and presumably keeps track of it so he doesn't accidentally sew up the scissors inside the belly of the patient. But in some sense, this is obsolete in the sense that this is invasive surgery, and more important as time goes by is minimally invasive surgery or even non-invasive surgery. So that brings me to this topic. Minimally invasive surgery, the concept arose as early as 1800, but it wasn't until the laparoscope and flexible endoscope were invented that it became feasible. Here you see on the left the person with two hand tools, each going through a hole in the belly. The belly has been inflated, and this arm here is holding a television camera. He's looking at what the camera sees, and he's manipulating things. Then the more recent version of that is to use robotics to hold the different tools. The operator then sits at a computer display, and furthermore, he has some image-guided capabilities so he can ask it to move to a particular location just by putting the cursor there. Now, once you get to a situation where the surgeon can be on the other side of the room, it's a small step to say instead, why can't the surgeon be 1,000 miles away? And obviously, this is of great interest to surgeons and the military, because surgeons do not particularly want to be on the battlefront. Let me mention in passing here that laparoscopic removal of the gallbladder has become the prevalent way of doing it. Almost 1 million operations a year are done these days using this technology. In the future, you can expect minimally invasive surgery in a magnetic field, where, of course, the scalpel and other tools have to be made out of plastic because the magnetic field is so strong. And in fact, I prepared this chart a long time ago, but just last week there was a report of some prototype of this in existence. So you can expect that. And you can also expect minimally invasive surgery using intestinal crawlers like this one here. You can see it can clamp on, has a biopsy needle over here for taking a sample, has a light television camera, and it just crawls through your intestines doing whatever it has to do. So you can expect that in the future to achieve reality. And then the final thing, in the distant future, you can expect minimally invasive surgery using nanorobots. But I want to be really, really clear here when I say you can expect this. You can expect it. I don't expect it. I think it's baloney. And so I doubt it. Now here's a wonderful medical robot, Sim1, built by Aerojet General in 1975, teaching medical students how to perform tracheotomy operations. The robot has pulse in the respiration. If you do the operation wrong, it dies, and presumably then automatically sues for malpractice. The more modern version is built by Gomard. Here's Hal, here's baby Hal, and here's Mama Hal. She's just had a cesarean section. You can see the wound here, and there's baby Hal in the background. And then there are rehabilitation robots of two types. One is to assist by replacing the muscle function that doesn't work. That's this. And the other one is to train muscles so that they work again. This happens to be a machine that gets strapped on to retrain a person how to walk after he's got some difficulty in walking. But I must say, I think that the people working on this training technology, they're missing the real big commercial application, which is that when it comes to weekend golfers, we are all disabled. And so wouldn't you like to be able to strap yourself into something and it would just teach you the perfect golf swing and everybody would immediately be as good as Tiger Woods? Here are some service robots from 1980, a mail cart that could follow a chemical line, and hospital delivery robots in the early days delivering meals and linen, but now also a teledoctor, so the doctor doesn't have to leave the comfort of his office as he interviews a patient. I'm sure you'd all love that. Now I come to the topic of military robots. In 2005, DARPA started this grand challenge of could a robot car drive all the way through the desert, 160 miles or so, and none of the robots finished. But the next year, there were lots of entries, 2005. Here are some of the entries. And the winner was Stanley from Stanford, led by Sebastian Thrun. Well, once that challenge got satisfied, DARPA created a new challenge called the Urban Challenge, which is to come up with a robot car that can drive around a city environment. And that contest will be held on November 3rd this year. And Stanford's entry is called Junior, and this is a picture of it. MIT and Stanford are the two favorites. Now, the military has been interested in other kinds of vehicles. In particular, they were interested in a walking truck that could be a truck, or maybe it could replace the tank. The problem with a tank is when it comes to a boulder-strewn field, the tank has to navigate around the rocks while the enemy is shooting at it. Wouldn't it be nice if the tank could leap over the rocks while shooting at the enemy? And of course, I think the fallacy here is these exposed hydraulic hoses here and here. You can imagine an enemy sharpshooter picking off the hose, and then pretty soon you'd have this thing limping along. Over here, at the same time, General Electric also built Hardyman. This was intended for construction workers so that they could just pick up heavy beams and bring them into place. And you may say, what is that doing on a chart dealing with military applications? Well, the answer is it finally saw a military application. Sigourney Weaver strapped herself into this in Aliens 2 in order to fight the alien queen. And let's see if we can get the sound to work here.
I'll be back.
There. Here are some more examples. These are military robots. 1984 and 2005. One hopes that when these robots are actually deployed in a military setting, one hopes that they'll be brave, not cowardly, like this one here. Here's another example of sort of military robots, BattleBots, which were popular on television for about 5 years. Here are some of the heavyweight champions during that period. But then along comes Isaac Asimov a number of years ago with the idea that robots should basically be benevolent and not hurt people. Number one rule, they may not injure people. Number two, they must obey orders. And number three, must protect their own existence. And out of that came the series of stories called iRobot, which deals with the ethical conflicts of these different laws. And the very last one of these stories in iRobot is about a giant machine called Megavac that could be considered a robot physicist, because it's been programmed to try to figure out a way of reversing the second law of thermodynamics. And Megavac computes away for billions of years. The universe is running down. All sentient beings have long since disappeared. And finally, Megavac comes up with the answer. And there's nobody to tell the answer to, so Megavac decides it'll try the answer. And so Megavac says, let there be light. And the universe starts all over again. So it's not just a robot physicist, it's a robot god. Now, household robots. This is a wonderful one, 1928, created by Westinghouse. It's really a speech recognition system. You yell into the speaker, into the microphone here, on. The vacuum cleaner turns on, and it gets this spot on the floor very, very clean. Well, that inspired a bunch of imitators. But all the imitators were joystick-driven systems, not autonomous systems. This is a hobbyist version in 1940. Here's a commercial version in 1980. So you could sit on your couch and drive the vacuum cleaner around. But then in recent years, you see actual autonomous robot vacuum cleaners, the well-known iRobot Roomba, and a few competitors, which I don't know if they're still around. Around the same time, one also sees robot lawnmowers. Here are a few of them, autonomous again, where you put some sort of a wire around the periphery of your lawn so it doesn't go running off down the block while you're sleeping. And it's a good idea not to let your baby play in the yard Then there are educational robots. There are lots of different ones here. I'm sure many people have seen some of them, and there are also lots of kits not shown here. And then robot toys are household robots. A few of the older ones shown on the left, one of the more recent ones on the right, and that goes to robot pets also. Sony Aibo, when it first came out, it cost several $1,000s to get a robot dog. There's a competitor, Isaibi, and then cheaper versions like the Wowie, which doesn't look that much like a dog. And then just recently, Sega came out with a robot chick, shown here, and you pet it and it moves its wings and cheeps. And then since I'm talking about animals, I thought I would include the robot cockroach from Case Western, the StickyBot wall climber built at Stanford by Mark Kotkowski and his group, and Roboraptor, which you can buy in lots of stores. Which kind of leads into the topic of entertainment robots. Well, here are some robot dinosaurs from a number of years ago. Here's a robot fish that swims by flapping its tail back and forth. And then there are stage shows in the spirit of Vaucanson's duck. Sabre 4 was built by a Swiss inventor, Auguste Huber, in 1939. In the stage shows, it would light somebody's cigarette, and it would roll around. In the corner of the stage, Auguste Huber was hiding behind a curtain, and he was controlling it with radio controls and making it speak and listen to the audience and so forth. And it reminds me so much of the movie, what's the movie where the line, oh, Wizard of Oz, with the line in it, "Pay no attention to the man behind the curtain." Westinghouse, same year, had an exhibit in the World's Fair in New York of Electro and Sparko. Electro had a number of talents, one of which was smoking cigarettes, which perhaps explains why he has not survived to the current date. Sparko was the dog, had a heat-sensitive nose. Now, I've read a rumor, which I do not believe, but I'll tell you the rumor anyhow. The rumor is somebody left the back door of the exhibit hall open, a car drove past, Sparko sensed the tailpipe, took out in pursuit, and got run over. In the same spirit, we see recent demonstrations of the Honda Asimov, a 26 degree of freedom machine that actually can balance itself while walking forwards, backwards, turning, going up a ramp or down a ramp, or up or down stairs. And don't get me wrong, the fact that it can maintain its balance while doing all those things is absolutely remarkable. But when they put on the stage show, they would have you believe that you're watching an artificial intelligence system that also can understand what it sees and hears. And it can't understand what it sees and hears. There's a man behind, or a woman behind the curtain running. Pay no attention. It's imitating his motions because somebody else is strapped into an exoskeleton with sensors that's doing that. Same thing here. It's shaking hands because somebody behind the curtain is making it shake hands. It's still a great technical accomplishment, but it's not what it seems to be. Now, actually, walking robots date all the way back to 1973. Ichiro Kato at Waseda University built this machine on the left. Humans, when they walk, use very little energy to walk. These robots use a great deal of energy to walk, and by comparison, recently, a couple of researchers have managed to build highly efficient walking robots where the free leg swings freely in an arc without using energy. There are some imitators. One of the notable imitators of Asimov is this one here. Also, some other major Japanese companies have gotten into the act building robots. They don't walk, but they have some similarities. This one on the right, I saw the description of the press conference where they demonstrated it. It put the package, picked up the package to put on the table 7 times, and the reporter reported that on the first 6 occasions it accidentally dropped the package. You don't generally see these kinds of accuracy in the reports. Usually you see only, oh yes, it put the package on the table, amazing. That's the difference between fantasy and reality. There are also robot musicians like this one. Somebody behind the curtain is telling it to bang away on the drums, or somebody here is running a program, and all of them are in sync. You can see through some radio link. So they appear to be playing the trumpet, but are not really playing the trumpet. They're just going through the motions. And here's another interesting application. Can you get robots to work as teams? In this case, the exercise is robot soccer. And here's a wonderful one. Robot dancers. You know, I'm really surprised that this has not appeared yet on Dancing with the Stars. I mean, it's just such a natural. But this brings me to the whole topic of female robots. Beautiful female robots. This concept arose first in the Tales of Hoffman, a story called The Sandman from 1815. It was the inspiration for the ballet Coppelia by Delibes in 1870. In it, the toy maker has gotten drunk, and meanwhile some teenagers have broken into his toy shop, and the girl is getting caught there, so she dresses up as a doll, and he's so drunk he doesn't realize, he thinks that she's really his doll come to life. Here's the 1927 movie, Metropolis, in which a mad scientist, Rotwant, has created a robot in the image of the heroine, Maria. And what he wants to do is instigate a class war between the managers and the workers. Turns out happily, though. And here's some other examples of female robots, beautiful female robots. The one on the right, the book was 1972. Many movies came out afterwards, so this is a more recent cover. But the book by Ira Levin is about a small town of Stepford, Connecticut, where the men, led by a former Disneyland technician, are slowly exterminating their wives and replacing them with robots that are in every possible way absolutely identical to their wives. Every way except one. They never get headaches. And then one also has the inverse theme, which is that of a human female with a male robot. And I'll only give one instance of that, but it's a really good example. If you've seen the movie Demon Seed, Julie Christie and the male robot, there's a scene in that. And I've been told, in the entire history of computing, that scene where that male robot seduces Julie Christie, entire history of computing, that's the only documented instance of a robot failure, a computer failure that can't possibly be blamed on software. Then we have puppets. Well, we don't consider these surprisingly animate, although very small children do. The first movie that had Yoda in it, Yoda was a mechanical puppet. But here are some recent puppets. Replier here, Kokoro Actroid here, and I think you can expect in the future in department stores to see the appearance of information booths with the Kokoro Actroid. So you'll walk up and you'll say, where are kitchen supplies? And the Actroid will say, that's on the third floor, the escalator's over there. Now I'll go through some scenes from the movie, chosen rather arbitrarily. Here's a very handsome robot on the left in The Phantom Creeps. Here's Mysterious Dr. Satan with Copperhead versus the robot. And here's a famous one, Gort, Patricia Neal, and Michael Rennie in The Day the Earth Stood Still. A robot so powerful he can destroy the Earth. But here's a very successful science fiction movie for its day, 1956 release, and this movie, Forbidden Planet, was a tremendous success. That's Robbie the robot in the middle. He appeared later on television programs. One of the reasons that this movie was so successful is that it's based on a very famous earlier play. I don't know if anybody knows who the author of the earlier play was. The earlier play was called The Tempest. It was written by William Shakespeare in 1611. Silent Running with Bruce Dern and the three small robots, Huey, Dewey, and Louie. Yul Brynner as the robot gunslinger gone crazy in Westworld. Peter Weller, part man, part machine. And here's Anthony Daniels, who's here roasting in the Sahara Desert inside this costume of C-3PO. And then, not a mechanical figure, but a figure with a vision capability, the robot HAL in 2001: A Space Odyssey. Here, Mission Commander Dave Poole and Frank Bowman have gotten into a pod to avoid being overheard by HAL. And HAL is looking through the window, reading their lips. And later,
I know that you and Frank were planning to disconnect me. And I'm afraid that's something I cannot allow to happen.
They want to turn him off, and they're not going to get the chance. Now you can even have robots, which are purely graphics animation, that the robots don't exist at all except on a piece of film. And now we'll get to hazardous environments. Robot submarine arms used for collecting coral to sell to tourists, or robot underwater vehicles used for exploring shipwrecks. Moving out from the sea, up into the air, and then up into space, we see some examples of robot birds. And then we move up to robot aerial vehicles, first with a military application, and some other smaller robots of the future, which will probably also have military applications. Moving out into space, You see robot arm here on the shuttle, and you see a robot arm here on the space station. And then, of course, there's this, the Robonaut from NASA, and some vehicles, or in one case stationary, but with an arm, some robots that have been sent to the moon or to Mars. And as a last example of a hazardous, well, next to the last example, is crawling into a volcano with a spider-like robot. Final two hazardous environments, one is putting out fires, and the other one is cleaning toilets. And here I will come back to the topic I mentioned earlier about the typewriter being redesigned so that a printer has a factor of 25 fewer parts. That's the case here. The toilet gets redesigned. You don't design a robot that knows how to carry a pail in one arm and a scrubbing brush in the other arm to clean toilets. Instead, you redesign the whole system so that the toilet is self-cleaning. I'm coming to the end of the talk. I only have 4 more charts, 3 with conclusions. First, the definition again. A robot is anything that's surprisingly animate, but what's surprising changes over time. So in some sense, we already have household robots, except we're not surprised by them anymore. Second, I'll spend a little bit of time on this. Don't expect intelligent androids in your lifetime. And some of you are pretty young in this audience, and I mean you. Motion dexterity is pretty difficult, but that's not the hard problem. Vision recognition is much harder than motion dexterity. You know, the Asimov robot has a vision system in its eyes, so in some sense it sees, but it doesn't understand anything it sees. But natural language understanding is much harder. Much, much harder. And by the way, that's not the same as speech recognition. People often confuse the two. Speech recognition is turning speech into text. Natural language understanding presumes that you already have the text. All you have to do is understand what the text says. If I were to write down this whole lecture and present it in text to a computer, there isn't a computer in the world that can understand what I've just told you, and you've understood it. Why is that? Well, it just starts out natural language is hard. But in addition, normally when people speak, they don't speak with good grammar. And bad grammar makes the problem much harder for a computer. But then it's really hard because robots work in a world of 3 dimensions, and it's very hard to describe 3-dimensional world in terms of words. And if you don't believe that, here's the exercise. Try to write a manual for how to tie shoelaces. And the idea is you want to write this manual and you want to send it to a Martian. He's never seen a pair of shoes in his life. He's never seen shoelaces in his life. But you've got to send him a pair of shoes, shoelaces, and a manual so he can figure out how to do it. It's incredibly difficult to do. And remember all the things that can go wrong, like the shoelace can break, or you can get it in the wrong holes or whatever. And then humans are very good at learning from example. But a robot, when it sees an example, it thinks, oh, that's what I have to do. And if it deviates from that one example in the slightest way, it doesn't know how to cope. So generalizing from examples is something that's not understood. So this is an enormous problem, at least 50 years worth of research, in my opinion. Number 3, the concern about weaving machines or putting in dips, notwithstanding, the social implications of robots are very small compared to the social implications of computers. Actually, when I used to present this talk, I would say that it's the job of computer scientists to figure out how to automate everybody's job except their own. But I got to say, with the invention of the internet, they've gone one step too far because they've now succeeded in some sense in automating their own jobs. Anyway, I'll conclude with this thought. The topic was fantasy versus reality and the future of robotics. And as I said in my opening statement, much has been written on the subject of robots. And a little of it is actually true. Thanks for listening.
So, David, thanks very much for a fantastically entertaining and educational talk. I think we've got time for some questions if anybody would like to ask a question to David.
Yes, whenever I've been involved with not really robotic applications, but movement type of applications, mechanical devices, it's always been a situation where the software and most of the parts involved, we've had to roll our own. And recently I saw an article in Scientific American by Bill Gates where he talked about a library, a software library.
Yeah, let me go in this direction because I guess that a lot of people can't hear you up front. But yeah, it's true that very often when you're dealing with robots, you have to design your own software. And there was an announcement out of Microsoft about 4 or 6 months ago saying that they were going to come up with a software library in the area. I haven't looked into it, so I don't know what the status of it is. I do know that I personally have tried to get some software out there that I've written. I'm finding it surprisingly difficult to get anybody to accept my software. And I think my software would make it a lot easier to do some of these projects. But it would be nice. It's difficult because each robot at the control level has very different kinematic structure. And then at the next level up, if you want to deal with the dynamics, everyone is different in terms of the masses and so forth. And then at the next level up, very often the tasks that you want to do are also very different. So it's not clear to me to what extent this library is really going to make life much easier. Hopefully it will. Any other questions?
Why did you express doubt about nanotechnology? You hear about it a lot, and you read a lot about it, and then you take on applications in medicine.
Yeah, there are, of course, a couple of movies. I forget what it was called. The Incredible Journey, I think, was. The question is, why am I so skeptical about nanorobots? And, you know, evolution is pretty good at coming up with machinery that does things on a very small scale. And humans are not so good at coming up with machines that do things, even on our scale, that appear to do things that are very intelligent or autonomous and so forth. To come up with something on the scale of a nanorobot that has any degree of intelligence not only says that you have to solve a lot of the intelligence problems on a big scale, you also have to figure out how to shrink it down to a microscopic scale. And there aren't at the moment any smart amoebas, in the sense, amoeba or paramecia or whatever. There are no small animals of that size that have the kinds of skills you want. And if you could find them, I think it'd probably be easier to train those animals to do the job. So, and let me also say that one of my assignments in the past 20 years or so is I spent a couple of years working in what's now called the Silicon Nanofabrication Facility at Stanford. So yes, I'm familiar with the claims that are made and so forth. But you know, you have to realize an awful lot of the claims that are made in the name of robotics or in anything else, where the claim is being made in an area where the person is being supported by government funds, very often the publicity is good because it increases the chance that they're going to get government grants to do their work. And it's nice to eat. So this creates a sort of a natural process where people create excessive expectation of what the capabilities are. I'm skeptical. I might be wrong. We'll see. Way up there.
Yeah, how long do you think will be before we have a robot that has the perceptual ability of the world around it, such as at the level of a mouse or a sparrow or something like that, a lower level mammal that interact in very interesting ways in the world?
I would guess 30 to 50 years, that's my guess. I remember seeing something at least 10 years ago where somebody was asserting that the robot he built had the intelligence of a grasshopper. I don't believe it. Grasshoppers are smart enough to reproduce. His robot wasn't. So, yeah, I'd say it's going to take a while. Yeah?
In Forbidden Planet, one way of looking at Robbie in there is as an articulate machine, because somewhat in contrast to the book, to iRobot, even though in that movie the robot is demonstrating the three laws, it's emphasized that this is purely an articulate machine, that there's nobody involved. What do you think of that as a direction for robotics rather than making, say, a synthetic human or animal with artificial intelligence?
I'm sorry, I just really don't understand the point that you're making. So.
Well, it seems to me that you could make a robot as an intelligent machine.
Yes, well, there are lots of robots which are intelligent in some very specific way. Robbie the robot was amazingly versatile in that particular program. I mean, he could understand speech, he could talk to people, and I forget what some of his skills were, but
Well, what I think of is a robot that, perhaps I shouldn't use the word intelligence, a robot that could be trained to work in an open environment where things move around, but would be able to recognize things and perform tasks based on where things currently are.
there are industrial robots that work on moving assembly lines that pick parts up that are not necessarily precisely positioned, and that these are commercial applications that work. So there's a degree here. As the environment gets more and more unstructured, it's much less likely that you're going to find a robot that can cope with it. But let me move on to another question. You can follow up afterwards. Yes?
How do they expect to run the urban automobile challenge without endangering the general public?
The urban automobile challenge is going to be run in some sort of a small city environment with traffic consisting either of other cars driven by people or possibly radio-controlled cars. There also will be impediments placed, like holes in the ground or barriers, which are not told ahead of time. And the assignment will be to go a distance of about 50 miles through this environment following some path.
That's a lot of artificial cars.
Well, I don't know how many there are, but it will have to be able to merge into traffic without a collision, and I'm sure that some of them will have collisions. It's a tough challenge, the urban challenge, but it'll be a long time still before something drives 23 miles to the airport. Yes?
Could you say that the first thing that we would get is automated intelligence on a computer where it simulates this environment and displays it perhaps in a graphical way, long before we actually have it move around the mechanism and make the mechanism work? And that's primarily what we're seeing here. The intelligent part is really software, not really the thing that we see.
Let me address this. You're saying that it's hard to build mechanical things that move in the real world of three-dimensional objects. Therefore, isn't it likely that we'll see an intelligent robot which is in graphic simulation moving around in a simulated 3D world? But let me point out that the problem of simulating the 3D world and dealing with the problem of collisions is a very complicated problem. In 2 dimensions, it can be solved fairly easily, that you can work out the motion of an object without hitting obstacles. But in general, this is called the piano movers problem. And as you get up to 3 dimensions, it's still reasonably tractable, although it's not obvious you can come up with an easy optimal solution just algorithmically, but heuristically you can. But as soon as you start allowing rotations, it gets to be an incredibly complicated problem. And then there's a lot of physics that you'd really need to simulate. For example, friction. How do you simulate friction in that kind of environment? Or if you bump into something, how do you simulate the fact that it's going to move, and if it moves off the edge of the table, that it's going to fall? Or that if it falls, that it may actually break in half. So it's really hard to do a real physical simulation of a 3-dimensional world in which you have a multi-degree of freedom robot moving. So not obvious to me that that makes the problem much easier.
David,
Yes.
Too many hands, too many questions going to be here all night long. So
Yes.
what I suggest is that David, I'm sure, will hang in, and I think maybe Nick will hang around for a little bit. And we have people outside who've got Ask a Physicist written on their chest, well, actually on a badge on their chest. I'm not sure how much they know about robots, but you can certainly try asking them. So please hang around and ask questions to David and the others personally. But before you go, big round of applause.